Welcome to Lecture 5 for Electrical Engineering 525. We begin this lecture by working on a problem from Section 3 in Chapter 3, which deals with monopole antennas. And the particular question that we will be working on first is problem 3.3-2. And it goes as follows. It says, for a thin monopole as shown in figure 3-10A that is a quarter wavelength long, A, rough sketch the radiation pattern in polar form as a function of theta if the monopole is along the z-axis, B, what is the directivity, and C, what is the radiation resistance. So the first thing let's do is to consider this figure 3-10A, which I have reproduced here. So here is our monopole antenna, and it is above a ground plane. And as is discussed in this section, we want to use image theory to solve this problem. So the image of that monopole is shown here. Now remember that the way that we image theory goes, if you have a current element above a ground plane, image theory tells us that we can take the ground plane away and put below where the ground plane was, put an equal distance below the ground plane the image current, and if we do that, the fields in the upper region above the ground plane will be the same as they were in the original problem. So here we're proceeding with that. Here is our original current element above the ground plane. You can see that the ground plane has been taken away, has been replaced by this dashed line, and then we've put in this image current below the ground plane, and it is just as far below the ground plane as the original current is above the ground plane. And another important thing to notice is that, how did we form the image current? Well, notice that any tangential currents that are tangential to the plane are reversed in direction, but any currents that are normal to the plane are unchanged in direction. So for instance, here, these currents along this segment of the original current, notice they're going from left to right, and that is tangential to this ground plane. And so when we form the image current of that portion, we will reverse the direction. And so you see that for the image of that, we have currents going from right to left rather than from left to right. However, for the vertical component of this original current, it's going in the upward direction, and since that is normal to the ground plane, we're going to keep, when we form the image of that, we'll keep the direction the same. So notice that here this current is going up, just as so this is for the image current is going up just as was the original current. So once again, when you form the image of a tangential current, you need to reverse directions, but when you form the image of a current that is normal to the ground plane, the direction is unchanged. So now here is our original current and the image current, and you can see that these two together actually form a dipole antenna. So image theory is telling us that if we come back up here to this original problem of the monopole above a ground plane, its fields in this region above the ground plane, now of course the fields below the ground plane will be 0, but for the fields above the ground plane, they will be the same as the fields that you would have in this upper region down here for a dipole antenna. And furthermore, we were told that this, remember, we're told in the statement of the problem that this is a quarter wavelength dipole. So that means that from the ground plane to the top of this segment is a quarter wavelength. And so for the problem down here for this dipole, it would be a quarter wavelength from here to the top, and then a quarter wavelength from here to here. So altogether, this is a half wavelength dipole. And we have information about the half wavelength dipole then that we will be able to use in this problem. So now we're ready to go ahead and proceed with the problem. Remember, the first part was to sketch the radiation fields, radiation pattern in polar form. Now, as we said, what image theory tells us is that the fields above the ground plane will be the same once you introduce the image and you take away the ground plane, but the fields below were 0, and so that's what we have right here. This is the pattern for a half wavelength dipole. This is the pattern above the ground plane, and then notice that we have nothing here below the ground plane. So that's the radiation pattern, and again, we get that from image theory. The second part of this problem, the B part, was directivity, and the formula for the directivity of a monopole above a ground plane is twice the directivity of the dipole. And so this is just 2 times 1.64. That value for the directivity of the half wavelength dipole is from page 75. And so we get the directivity of the monopole is 3.28, or in dB, if we take 10 times the log base 10 of that, we get 5.16 dB. And then finally, part C for the radiation resistance. The radiation resistance of a monopole is half of the radiation resistance of the corresponding dipole. Again, this is for a monopole above ground plane. Is half the radiation resistance of the dipole in free space. And so in this case, that would be 1/2 of 73 ohms, which is 36.5 ohms. Now, you might say, how did you get this 73 ohms? And that was a couple of steps to do that. On page 74, we are given that the input impedance of a half wavelength dipole is 73 plus J 42.5 ohms. So from that, we see that the input resistance is 73 ohms. It's the real part of the input impedance. So the input resistance is 73 ohms. And from page 60, we're told that the radiation resistance is equal to the radiation efficiency times the input resistance. And finally, from page 74, we're told that the radiation efficiency of a half wavelength dipole is very close to 100%. And so if that's the case, then the radiation resistance is essentially equal to the input resistance of the half wavelength dipole, which we have already concluded is 73 ohms, and therefore that's how we obtain this value of 73 ohms for the radiation resistance, which we then used up here in this equation to find the radiation resistance of the monopole above a ground plane. So that's how we got this value of 73 ohms. And that concludes this problem, which is, it just gives us a little bit of exposure to the monopole, the grounded monopole antenna, and, or excuse me, the monopole above ground plane, and also gives us a little bit of review of image theory. Now, in the next problem, which comes, it covers material from section 4 of chapter 3, we're going to have a problem about a small loop antenna. And in this problem 3, this should be actually 3.4-2. So let me change that real quick. 3.4-2. We're asked to verify that the power radiated from a small loop is given by this formula here. P is equal to 10 I squared times the quantity beta squared S quantity squared. So from equation 2-127, we have that the radiated power is 1/2 the real part of the integral over some surface S sub P of E cross H star dot ds. And S sub P is any sphere enclosing the antenna. So we can make life easy by choosing the sphere to be in the far field, and that allows us then to use the far field expressions for E and H. And remember, this star represents conjugation. We're going to take the complex conjugate. So taking this sphere to be in the far field and using the far field expressions for E and H for a small loop antenna, here's E and H in the far field for a small loop antenna. And by the way, notice that these fields are the dual of what we have for the ideal dipole antenna. In other words, for the ideal dipole, we saw these. We saw that E had only a theta component and H had only a phi component, and now that situation is exactly reversed for the small loop antenna. So, resuming then, if we plug those values in to the expression for the power, we get that the power is 1/2 the real part of eta beta squared S times the I e to the minus j beta r over 4 pi r sine theta times phi hat cross minus beta squared S I e to the j beta r over 4 pi r sine theta theta hat dot ds. And that should be a vector quantity there, that ds. So let's correct that. Now, if we take out of this integral everything that's constant, well, eta is constant, beta squared is constant, S is constant, I, the 4 pi in the bottom here, this beta squared and S and I and 4 pi. So if we take all of that out, and we also use the fact that phi hat cross theta hat is minus r hat, and then we have a minus sign here, so the minus of minus r hat will just give us r hat. So we have, this is where this r hat comes in. You see all of the constants that we've taken outside of the integral. And inside the integral, we have a sine theta times a sine theta, and then r and r. So sine squared theta over r squared. Notice that e to the minus j beta r times e to the j beta r. Where did the e to the j beta r come from? Well, because we took the complex conjugate of h, and so that this e to the minus j beta r in h became e to the positive j beta r in h conjugate. So when we multiplied this e to the minus j beta r times e to the positive j beta r, that went away. And so we're just left inside the integrand with sine squared theta over r squared, then the r hat coming in from phi hat cross negative theta hat. And now where did this r hat come in? Well, from ds. ds is equal to r hat r squared sine theta d theta d phi. Of course, r hat dotted with r hat is 1. The r squareds here cancel. And so we're just, and after we do all of this, we see all of this inside the brackets is real, so we can drop that part. And we're just left with this expression here, and we have to do a fairly easy integral, which is the integral of sine cubed theta. The easiest way to do that is to rewrite sine cubed theta as sine theta times sine squared theta, but sine squared theta is the same thing as 1 minus cosine squared theta. So we have the 1 minus cosine squared theta here, and here is sine theta, and we're integrating from 0 to pi. And so we break that up into an integral from 0 to pi of sine theta d theta minus an integral from 0 to pi of cosine squared theta times sine theta d theta. And of course the integral of sine theta is minus cosine theta. And here this has almost the form u to the n du. We just need a negative sign on the inside, which we can take actually from the outside, so that this becomes plus, and take this negative sign on the inside associated with the sine theta, so that becomes part of the du. So here's u to the cosine of theta is u, so we have u squared du, and therefore the integral is 1/3 u cubed, or cosine cubed over 3, and we're evaluating that from 0 to pi. So when we evaluate everything inside the brackets, we get a 2 for this first term and a negative 2/3 for the second term. So altogether 4/3 here, multiplying this constant. And so this ends up to be eta beta to the 4th s squared I squared over 12 pi. And as you probably remember from a previous course, for free space, eta is very close to 120 pi. So if we substitute 125 pi for eta and then bring down everything else, this ends up being 10 beta to the 4th s squared I squared, or 10 times the quantity beta squared s squared times I squared. And that was the desired result that we were asked to show. So that's how that would go. And now let's do one more problem on this section with loop antennas, and I'll be asking you in your test to do a very similar problem. It says a single turn circular loop antenna with a radius of 0.5 meters and made of number 8 AWG copper wire operates at 10 megahertz. And then you're asked to calculate several quantities: A, the radiation resistance; B, the ohmic resistance; C, the radiation efficiency; and D, the input reactance. So let's see how these calculations would go. A, we want to calculate the radiation resistance. Well, from equation 353, we have the radiation resistance is 31,200 times S over lambda squared quantity squared, and that gives us the radiation resistance in ohms. Now S is the area enclosed by the loop, which of course will be pi r squared. And we're told in this case that the loop had a radius of 0.5 meters. So we have pi times 0.5 meters squared, or 0.25 pi meters squared. And again, as I mentioned in an earlier problem, in an earlier lecture, I strongly suggest that you carry around the units. Because as you can see in this problem, we're going to be dealing with millimeters and meters, and so if you just drop those units, you almost certainly get into trouble. So S is equal to 0.25 pi meters squared. Now lambda is C over F. C is 3 times 10 to the 8th meters per second. F is 10 megahertz, so that's 10 times 10 to the 6th inverse seconds. So we have inverse seconds in the bottom canceling with the inverse seconds in the top, and all we're left with is meters in the top, and that looks great because after all we're calculating a wavelength, so meters does look like the correct unit. And then 3 times 10 to the 8th divided by 10 times 10 to the 6th is 30. So the wavelength is 30 meters. And now if we take these values for S and lambda and plug them into this formula for the radiation resistance, notice that we're going to get cancellation in here, and then we have this unit of ohms out here, which was in the original equation. So everything turns out right here for the expected units for the radiation resistance, and we get this answer of 0.02376 ohms. Now in part B, we're asked to find the ohmic resistance. Now, in a previous case, the book used the symbol R sub O for ohmic resistance, but for these circular loop antennas, they're using RW for the ohmic resistance of the wire making up the antenna. So anyway, the formula that you have from equation 359 is RW equals B over A times RS. Now, what do all these quantities mean? Well, B is the mean loop radius for the loop antenna. A is the wire radius, and R sub S is the surface resistance. Now, how do we get these values? Well, you have to look in one of the indices in your book. And namely, if you look on page 783, you'll see that for number 8 AWG copper wire, the diameter of the wire is 3.264 millimeters. Now, as we said, A is the radius of the wire, so that will be 1/2 of D, or 1.632 millimeters. From the same page, we have sigma for copper. Remember, this is copper wire. Sigma for copper is given by 5.8 times 10 to the 7th Siemens per meter. Remember that a Siemens is an inverse ohm. Now, the reason that we went ahead and noted this conductivity is that, as you can see here, this ohmic resistance that we're trying to calculate depends on R sub S, the surface resistance, and our formula from equation 2-171, our formula for the surface resistance is square root of omega mu over 2 sigma. So that's why we wanted to go ahead and find sigma and note it as well. So now we plug in everything for RS, and we're going to make sure all the units work out okay. So omega is 2 pi F. So that's 2 pi, and remember F is 10 megahertz, so we have 10 times 10 to the 6th. And this S here, this is not Siemens, this is seconds, it's hertz, so seconds, inverse seconds. And then mu is 4 pi times 10 to the minus 7th henries per meter. But remember, we found out in lecture 4 that a henry is an ohm second. And so we have ohm seconds and then meters to the minus 1. In the bottom, we have 2. And then this quantity we got from the index, 5.8 times 10 to the 7th Siemens per meter So the per meter is right here, and Siemens, as we said, is inverse ohms. Now look at these units inside the radical, and let's make sure everything is going to come out right. Inverse seconds will cancel with this seconds, so that goes away. This inverse meter will cancel with this inverse meter, and we're left with ohm in the top and inverse ohm in the bottom. So when we multiply top and bottom by ohm, we have ohm squared in the top and dimensionless in the bottom. So we have ohm squared in the top, and then when we take the square root of that, we'll get ohms. So this is perfect. This is exactly what we expect, that we get units of ohms for the surface resistance. If we take then all that's remaining after we do that is just numbers inside the radical, and so if we do that calculation and take the square root, we finally get RS is 8.25 times 10 to the minus 4 ohms. So that's the surface resistance. And now that we have the surface resistance, we're ready to finally calculate this ohmic resistance, R sub W. And the formula for that again is B over A times RS, where B is the loop radius, A is the wire radius, and RS is the surface resistance. So we have 0.5 meters for the loop radius, 1.632 times 10 to the minus 3 meters. Remember, that was 1.632 millimeters for A, but you know, we since we have meters in the top, we want to put A in terms of meters as well. So 1.632 times 10 to the minus 3 meters. Again, I just emphasize it really is important for you to carry along your units. And then RS, we've just calculated, is 8.24 times 10 to the minus 4 ohms. And when you do this calculation, you get that the ohmic resistance is 0.253 ohms. And now for the efficiency, the radiation efficiency, we have from equation 2-178 that the radiation efficiency is equal to the radiation resistance divided by the sum of the radiation resistance and the ohmic resistance. And as I've already noted, for this particular problem, we're using RW for the ohmic resistance instead of R0. So then the equation becomes R sub R over R sub R plus R sub W. And plugging in the values that we've calculated above for the radiation resistance and the ohmic resistance, we get an efficiency of 0.086, or in other words, 8.6% is the radiation efficiency. And then finally, we're asked to find here if you look part D, the input reactants. So we come back down here to finish up this problem and this lecture. The input reactance X sub A is 2 pi F times L, the inductance, where from equation 3.62, that inductance is equal to, for a circular loop, is equal to mu B times the quantity log of 8B over A minus 2. And we've already been introduced to all of these quantities in this equation, so there's no need to discuss them again. Okay, again, mu is 4 pi times 10 to the minus 7 henries per meter. B is 0.5 meters, and then this is the log of 8 times 0.5 meters over 1.632 times 10 to the minus 3 meters, and then minus 2. And if you turn the crank on this, you get L, the inductance, is equal to 3.65 times 10 to the minus 6 henries. So the input reactance, as we set up here, is 2 pi FL. So this is 2 pi F, again, is 10 times 10 to the 6 inverse seconds, times L, 3.65 times 10 to the minus 6. And now we'll go ahead and write henries as ohm seconds, so that second will cancel the inverse seconds in the frequency, and we're then just left with ohms, which is correct for the input reactance, and our final value for the input reactance is X sub A equals 229.14 ohms. So that concludes lecture 5, and we're going to do something just a little bit different this time. On test 5, the first problem is going to be here at the end of the video. And so let me explain that problem, and then there will be a second problem on test 5, which will be given in class. So problem 1 is as follows. We consider a current element above a ground plane, and it's shown here. And the question is very simple, really. It just says, which of the following pairs of current elements will give the same fields above the plane? So you have 4 here in A, B, C, and D. You have 4 pairs of currents shown. Here's one pair, and in each case these are dashed lines, so that represents that the ground plane has been removed. And we want to know which pair of these 4 pairs of currents, there's only one that will give the same fields above the dashed line as this current element does give above and in the presence of this ground plane up here. So which of these 4 pairs is the correct pair to use for this problem? So it's just A, B, C, or D. And the statement of the problem, these pictures here, will not be reproduced on test 5. So you need to put it in your notes, or go ahead and work the problem right now and write down the answer so that you can put it on the test when you come to class. And then again, so that will be the first problem for test 5, and then there will be a second problem as well, and I'll go ahead and tell you it will deal with this problem that we were discussing here at the end of the lecture, which again is this problem 3.4-7. What I'm going to do is give you a very similar problem with a different, actually it'll have all the same quantities, except instead of number 8 AWG copper wire, we'll have another type of copper wire that will be used. So you can work that problem just to get a little more practice with this procedure. But that's it then, and that concludes lecture 5, and good luck.